Hello, everyone. Today is June 7th. We will go ahead and get started. So the goal today is to finish chapter 5, the PowerPoint notes, and then to go on to the homework. So we'll see how we get on the homework. If we finish the homework will still be due today. If we don't finish the homework, then the homework will be due tomorrow. So we'll go ahead and get started. Does anyone have any questions for me before I go ahead and get started? All right. So yesterday, we talked about that the molecule on the top right. I'm going to get my pen out. This has a mirror plane. So because it has a mirror plane, it's going to be achiral. So if a molecule has a plane of symmetry, it will be achiral. Now this one doesn't have a plane of symmetry because if it did, this would be here and this would be here. But we don't have that situation, so we don't have that plane of symmetry. It says molecules with an even number of chiral centers that have a plane of symmetry are also called mesocompounds. So another way to test if a compound is a mesocompound is to see if it's identical to its mirror image. And yes, it is. So draw the mirror image of the cis isomer and show that it can be superimposed. By definition, when a compound is identical to its mirror image, it is not chiral, it is achiral. We did establish, why this was achiral. Compound has a plane of symmetry, it is achiral. So, but a compound that lacks a plane of symmetry may still be an achiral compound if it has a reflection symmetry through an inversion about a central point in the molecule. Since the molecule to the right has two chiral centers, and the chiral centers are here and here, and no plane of symmetry because it doesn't have any plane of symmetry, but it still is achiral because of inversion. So overall, the presence or absence of rotational symmetry is irrelevant to chirality. A compound that has a plane of symmetry is achiral, and we saw that class example, that achiral compound, that cis compound. A compound without a plane of symmetry will usually be chiral, but there are exceptions, such as a compound with an inversion center, and they showed us that this compound has an inversion center. So it says these compounds below are mesocompounds. So a compound with chiral centers, what is achiral because of symmetry? You can easily see, here's your centers. It's this plane of symmetry right there, and I try to draw it for you. Because mesocompounds have less than the predicted number of stereoisomers based on the 2N formula. So it's not gonna, so we used this formula before. Remember, for cholesterol, we found it had 8 chiral centers, so it was 256, but this is not gonna work for this. Fisher projections can also be used to represent molecules with chiral centers. Here you see the chiral center right here. Horizontal lines represent coming out. So if you see the horizontal, so this is the horizontal line right here. And it's coming out, and that's why they depict it right here. See that solid wedge? It's coming out of the screen. And then the dash wedge means it's going into the screen. So the vertical lines are going back into the page or into the screen. And then they give us some examples of some Fisher projections. You know, here's 2 chiral centers, and you can imagine here's 3, here's your 4. And then these ones right here, remember they're coming out of the screen, so you could represent them like this. And then the ones vertical, they're going back like that. And you could obviously draw on all the other wedges, but you know, I think that's a fit. Does anyone have any questions on that? So Fisher projections are also useful to quickly assess stereoisomeric relationships. Here we see we have enantiomers. They're mirror images of each other. If you flip these, I guess let's just flip that 90 degrees that way, 90 degrees that way, we'll be with bromine. That we'll have the hydrogens, and we'll have the R1 and R2. But if we do the same thing here, we're tied with bromine and hydrogen and bromine and bromine. That's okay with bromine and bromine, but you know, we don't have a mirror image here. We don't have a mirror image here. So that's where we're not having a mirror image. So we are stereoisomerism. All right. So molecules can rotate around single bonds. Recall the gauche rotational conformations of butane. Remember, you know, there's one carbon here, and then there's one carbon behind that we're not seeing. I just wanted to point that out. So realize these conformations are chiral and are actually enantiomeric. But because these rotamers are interchangeable by bond rotation, butane is not a chiral compound because these bonds can keep on rotating. That's what they're saying right there. You know, yes, you know, we can see this mirror plane, but it could just, this methyl group could rotate over here, and now it'd be identical. So that's why it's, you know, they're not chiral. So here they're wanting us to compare the Cheer conformations of cis-1,2 dimethyl cyclohexane. Cyclohexane means 6. And if this is a 6-membered ring right here. Dimethyl means we have 2 methyl groups. Here's 1, here's 2. And we do have a mirror plane. These conformations are chiral and are also enantiomeric. I shouldn't say we have a mirror plane. They mirror each other is what I should. That's a proper term. However, these conformations interconvert, and overall, this is an achiral compound. They possess a plane of symmetry. Because this can interconvert up like this. And if it interconverts up, then we have that plane of symmetry right here. That's what they mean by that. Atropisomers or stereoisomers that would be interchangeable through the rotation of a single sigma bond, but because the bond is unable to rotate, the different conformations are stuck and not interchangeable. So R and S BNAP are chiral and enantiomers of one another, even though they do not have. So this is more of a specialized form that someone did some research on. So here's the S form, here's the R form. They don't have any chiral centers, but they have an axis of chirality, and you can see this right here. They can rotate on this axis. Allenes are compounds that possess two adjacent carbon-carbon double bonds. They may or may not be chiral depending on the substituents. The two groups on each end of the allene are different, then it will be a chiral compound. We can see that they are different right here. And we do have enantiomers. We can easily see this mirror plane. Because if you rotate this one 180 degrees this way, that methyl group will be here through a 180-degree rotation. The hydrogen will be here. So you can now see kind of how they're enantiomers. It says most methods of separating compounds from one another take advantage of the compound's different physical properties. Distillation, that's a separate, these are just separation. This is a separation technique. Separation with different boiling points. A recrystallization, it separates compounds with different solubilities. It says such methods often don't work to separate one enantiomer from its racemate. That means it's separating the R and the S, but because they have identical physical properties. Remember, they have identical boiling point, but they have different pharmacological attributes, and there are ways to separate those out, but not through this distillation or recrystallization. It said Pasteur performed the first resolution of enantiomers from a racemic mixture of tartaric acid salts. And they call them salts because you have this negative and you have a positive and you have a negative and a positive here. The different enantiomers formed different shaped crystals that were separated by hand using tweezers. So he separated out stuff using tweezers, but there's more sophisticated methods, but you still can do that. Another method is to use a chiral resolving agent. The different physical properties of diastereomers allow them to be more easily separated. So you have this pair of enantiomers, right? If you put them on top, that amino group will be behind. If you react it with this, we're going to get this right here. We'll call it compound 1. Will give you these compounds, and compound 2 will give you these compounds. So we could separate them out. It says affinity chromatography is often used to separate compounds. You have a glass column, you pack with a solid substance. So you have a glass column, you pack it with some type of solid substance like this. It's going to go all the way up, reach about here. If a chiral adsorbent is used, then enantiomers will interact with it differently. So this might interact more with the R and let the S pass through more quickly, while the R stays behind. And that's what they mean by that. At first we'd start with R and S here. And then over the separation, the S is going to come out because it doesn't absorb to that adsorbent as much. And that R, it's going to stick to that adsorbent more. So you can see a separation difference right here between R and S. So for molecules with different groups attached to the carbon-carbon double bond, the EZ notation is used instead of cis-trans. So for molecules with different groups attached to the carbon-carbon double bond. So cis-trans isn't adequate to differentiate between these two diastereomers. Cis and trans only works if there is a like group on each carbon. And here we see that there's different groups, so we're going to have to use a different designator called the E and the Z. So it says F gets priority over carbon. This is a good time to get out your periodic tables. You can see F. If you look at your periodic table, I just got mine out. You'll see that fluorine, is atomic number 9 versus atomic number, for carbon it would be 6. So 9 is bigger than 6. So we're going to pick. That's why you pick fluorine. So here's fluorine. Here's carbon. We're going to pick fluorine. Here we have nitrogen. So nitrogen is going to have the priority over hydrogen. So this will be the Z designation. Z for same side. So here you have Z, and here you have E because we just flipped the nitrogen. So it's kind of like the trans, but it's on opposite sides, right? So it's kind of similar to trans, but the difference is we have different. It says cis and trans only work if there is a like group on each carbon. Here we don't have like groups. We have different groups in carbon, so we're going to use the E and the Z designation or designators. So hopefully that shows you why we have Z and E. And that's it. So I need to pull up the homework. I'm going to get the homework right. I'm going to pause the recording. I'm just going to pause the recording. All right, we're resuming the recording. We're going to start the homework now. So let's go ahead and get started. Here's our PowerPoint slides. We're on chapter 5, so hopefully you had some time to pull out the chapter 5 homework. And like always, we'll start on question 1. So for question 1, pull my pen out. Question 1 has 4 different options. It's going to be a top left, top right, bottom left, and bottom right. It says, can the top left compound exist as stereoisomers? And we're going to select yes. And that's because the 2 alkene hydrogen atoms are different carbon atoms, so are on different carbons, so the compound exhibits cis-trans isomerism. Now let's go to the top right, and we're going to select yes for that one too. This is going to be my grid. So for that compound, there are 4 different groups: methyl, hydrogen, bromine, and ethyl bonded to the alkene. So this group will exhibit stereoisomerism. Let's work down here. We're going to press yes again. And the reason for that is the 2 chlorine atoms are on different alkene carbon atoms, so the compound exhibits stereoisomerism. And for this one, we're going to press no. That's because 2 ethyl groups are bonded to the same alkene carbon atom, so the compound will not exhibit cis-trans isomerism. So that's question 1. Yes, yes, no, and yes. Hold on 1 second. Let's go on to question 2. Let's see, question 2. Question 2 says determine whether a nail would be chiral or achiral. A nail is usually achiral. Question 3. It has, oh, let me draw that over. I'm going to move this little thing. Oh, you can't see it, but it was in my way. It says, what is chiral? What is achiral? Achiral means I'll have a mirror plane of some sort. A nail, a baseball bat, wooden spoon. I'm just going to put spoon. If we select, remember, a glove is usually right or left-handed, a left ear, a snail shell, and a right foot. So I'm going to let you guys copy that down. So someone put something in the chat. So a screw would be chiral. The nail is not chiral because the nail just has, so the nail just has this, that's a bad nail. It just has some type of point, right? But a screw would have, I'm going to try my best. It has some type of thing like that down it, right? So that would be the difference between a nail and a screw. So I'm going to just leave that there. All right, so we have chiral and achiral. So hopefully that answers that. Let's go on to what question? That was question 3. I better write the question number here. We'll put it in this corner right here. Question 4 is which compounds can exist as optical isomers or enantiomers? And we have to select the ones that have chiral centers. So we're going to select 1 and 2. You're not going to select 3 because there's 2 methyl groups and 2 chlorines coming off that silicon. So that's why we're not selecting the bottom one. Here we have question 5. In question 5, they want you to select how many chiral centers this has. Basically, a chiral center is something that has all different substituents different coming off of it. I think I have everything. So we have to try to identify how many different chiral centers there are. So let's just count 1, 2, 3. Oh, that looks like a bad 3. 4, 5, 6, 7, 8, 9. So the answer is 9. So let's go to question 6. It says indicate whether the molecule is chiral or achiral So achiral means it have a mirror plane or a lot of the same substituents. This has everything different, so we're going to press chiral. So you want to select chiral for that one, 6. Seven, I'm going to put 7 on the same slide. It's the same kind of question. It says indicate if this is chiral or achiral. Again, we're going to select chiral. Question 8 can even be written on the same slide. It says question 8 says which structure contains a plane of symmetry. Well, plane of I'll draw this one, and then hopefully you'll be able to infer which one is next. This has a plane of symmetry here. So you're going to select this one. You're also going to select the second one too, because that plane of symmetry will be going, down this way. So you select 1 and 2. And then it says which molecule is chiral. That means it doesn't have so if we selected the ones that have a mirror plane, we already selected the ones that are achiral. So the only one left is option 3. So you're going to select option 3, because that doesn't have a mirror plane. So that's going to be chiral. Question 9. And I'm not going to draw the whole structure, I don't think, but you're going to have a structure that has this, then it has this H right here, and you have this, and you have some type of R group coming off. That's different. And we have to select whether this is the R or S. So since this R group is bigger, we'll just draw, it's not much to draw at all. So this would be 1, 2, and then 3. Okay, there we go. This is 1, this is 2, this is 3. And why did I not select this one? Because this one has, here's 2 carbons right here. That's why I selected this one as 1. So 1, 2, 3. This is S, but then it flips. Why does it flip? Because you have the hydrogen in front. So then it's R. That's A, and then B. Let's see. That's a good time to get out your periodic tables. So we have 1, 2, 3. And this would be, it's going in this direction, so this would be S. Here we had to pick oxygen first because that was the largest one, followed by nitrogen, followed by this 3 group, and then this would be priority number 4 right here. So that was 9. So you're going to select R for here, S for here. For 10, it says indicate the stereochemical configuration for the tetrahedral centers below. So they show you 3 sites. So site 1, this. here's site, they call this site 1, they call this site 2, and they call this site 3. And it wants us to determine whether it's S or R. So let me see. For this one, for site 1, let me see. We have nitrogen, which would be priority 1. Then we come 2, 3. This would be the S designator. This one would be 1, 2, 3. So this would be S because this would be. So site 2 is also S. Because if you come to the right, then you come into oxygen. You go to the left, you come into nitrogen. So this would be S. And site 3 would be 1, 2, 2, 3. Would also be S. So they're all S. So that's 10. Question 11. It says they give you a 3D molecule, and you have to determine, which one has the higher priority. The higher priority will be the cyclo group. This is your C5H9. The lowest priority coming off of that, and you have to turn it around to really see it. The lowest priority will be the hydrogen. So that'd be hydrogen. It says name the structure. So if we now look at, the order of priority and you put the hydrogen in the back, I'll do that myself. I'm using the 3D structure. So 1, 2, 3, we're going to be in the R position. So there's only one R choice that you can pick. So it's R4 cyclopentyl octane. My question, okay, I was going to say my question 12 wasn't loading, but it finally loaded up. Question 12, they give you a 3D image. If you draw, oh, doing that right, yeah. Oh, so I drew the 3D image for you. It erased on me for some reason right there, but that's okay. We'll just redraw it back. We just have to name that compound.
What are you doing?
I'm gonna rotate it myself again. Okay, this one's a little more complicated. I'm going to redraw this structure. I know I'm going to put the hydrogen coming out, but that's okay. We can always flip our answer. Oh, yeah, the hydrogen's coming out. That means I'll have a solid line. Try to flip your structure so you can have it kind of like mine. So the chiral centers are here and here. So let's determine, here's the nitrogen, here's this. I'm looking at this one right here. There's an update on your screen. Okay. This update, I have no control over this update. This is, so I apologize for this. I'll try to move this, but I have no control over that update. The Eastern Kentucky University is mandating that I get that right now. So I do apologize for that. Can everyone see my screen? Okay. I do apologize for that update, but that's just, when you work for a company or institution, sometimes they'll do these automatic updates and you don't get a lot of control over what happens because this is not my computer. So we have this chiral center right here. I'm just looking at one. It's not going to be one, but I just want to designate it one, and I'll designate this chiral center two. That nitrogen would be first. So we go 1, 2, 3. So this would be an R then, right? If we go this way with the hydrogens coming out, that'd be R. And now we look at this 2 right here. We'll go 1, 2, 3. That would be R. Let's see. I might be using myself. Let me just think about this. One. Okay, so this goes this way. Sorry about that. If it goes this way, because the nitrogen is 1. This 1, 2, 3. This would be a propyl group. This would be an ethyl group. So we're going around this way, counterclockwise. This would be R. So I do apologize. That's R. Now I'm looking at this one. This would be 1 here. This would be 2, 3. I go clockwise. We have to flip it because the hydrogen's coming out. So this would be S. So the name is 2 S, because this is the 2 position for the butoxy group. 3R, because this would be 1, 2, 3, 4, 5, 6. So you have a hexane. So you have 3R, 3 position, and you go 2, comma, butoxy, hexane. So I know this was a more difficult question, but that's the answer, and hopefully that makes sense. Yeah, so someone wants me to go through the naming. So we have a butoxy group on top. Let me go back to the question. It's going to load up for me. Put it in. And sorry about that. I had this all confused. This is not a nitrogen. This is an oxygen. I really do apologize. It won't change the answer. I don't know why I was thinking that was nitrogen. I really should. So red is oxygen, and for some reason I was thinking that's nitrogen, but that's oxygen right here. It doesn't change our answer though. So we have we have a hexane group on the bottom, right? This is your hexane group. And at the 3 position, we have a stereocenter. And we have to determine, whether that stereocenter is R and S. So, that oxygen is going to beat, see, in my case, nitrogen would beat carbon anyway. That's how it worked out. But that oxygen is going to beat, this propyl group, which is higher than ethyl group. So you go the butoxy group, then propyl, then ethyl. That goes in an S formation, but we flip it because the hydrogen's coming out. So that's how you get the R. Then with the butoxy group, bu means 4, so you have 1, 2, 3, 4 carbons. This is what I'm looking at right here. You have a 4 carbon group. That's how you get the butoxy. This is going to be at the 2 position, 1, 2. You have that oxygen coming off. That's how you have that 2' right there. And this is going to be an S just because of the designator. So we go oxygen, the 2 carbons, then the single carbon. So you go 1, 2, 3. That's an R, but we flip it to the S. That's how we get 2' S, and the prime is that group coming off, comma 3R dash. At the 3 position, we have that butoxy group. So 2' dash butoxy hexane. So that's how this naming comes about. All right, you're welcome. So good thing we did go back because I had that oxygen and nitrogen. I just wasn't reading the colors correctly. So 13, it says select the IUPAC name for the compound, including the R and S designation. So why don't we do that? We have that hydrogen going back, so that'll make it easy for us there. We have this group coming off, and we have this. So we know it's going to go priority 1, 2, and 3. So this is going this way. It's clockwise. So we know we're going to have the R is going to be our designator. And at the 3 position, 1, 2, 3, we have a methyl group. So it's 3, so R3 methyl hexane. And it's hexane because we have a 6 carbon group, right? We have 1, 2, 3, 4, 5, and then 6. $14. Come kind of similar. Select the correct R or S designation. We're not going to select anything because I'm not going to draw the whole structure out, but you have 2 OH groups, right? So if you have 2 of the same, you're not going to have R or S. So we can't have R. We're not going to have S. No, we're going to have none. None of the other choices. So we're going to select none. So 15, we're going to have to add the dashed solid wedges. And they're saying that one is the active ingredient of ibuprofen, the other one is not. It says only the S is the active ingredient. So if you do the S, you should be able to do you should be able to do the R because it'll just be flipped. The only thing I'm going to do is put a solid here. I'm going to put a dashed here. So this is going to be your R. I mean your S. And the R is just going to have this flipped. You know, these two groups will be flipped for the R. You know, where the hydrogen will be solid and then the methyl group will be going behind. That's all you're going to do for the R. This would be designated 1, 2, 3, and that's how you get the S right here. And the R is just flipped. Any questions on that? All right. 16. It says consider the stereochemistry of the compound and its relation to optical activity. The compound is going to be optically inactive. It's going to be, you know, this is it doesn't have any chiral centers, so this is going to be optically inactive. So we're going to select inactive. There's 3 chlorines coming off of it. And if we get finished with the homework earlier today, I always think we're going to get done earlier than what we do. We're going to be done for today. We're not going to move on to chapter 6, but I will load chapter 6 at some point in time today. That way you have it for tomorrow. And this week, this will be our last week. I think this is our 3rd week. Let me think. Yeah, this is our 3rd week because I'm in my 3rd week of summer school too. I took two tests already in my class. You're lucky that I don't assign a test every week like my professor does. So yeah, I had a test my 1st week, a test the 2nd week. Now I have a test this week. So this is our 3rd week. So you will after this week, you know, this will be the material that is on for the exam 1. So whatever we finish this week will be on exam 1. Let's see. Question 17. Says draw the unique stereoisomers for 2-chloro-2,3-dimethylpentane. Class I'm taking right now, you know, I really empathize with you guys. I'm going to give you more time than 25 minutes to do your exam. That's all we have. We have 25 minutes to do a 20-question exam, and you really, really have to know your stuff. There's not a lot of time to be looking stuff up. That clock just keeps on ticking, and it puts pressure on me that I don't really enjoy. But you know, so I feel how you guys feel. That's why I give you more time than what you need, because you know I'm in those situations. I don't feel, you know, something that I don't want that kind of pressure on you guys either. So we drew the unique stereoisomers for 2-chloro-2,3-dimethylpentane. And the only difference is, you know, is this right here. So we have 1, oh, my pen's not working. For some reason, my pen has stopped working. Here we go. So 1, 2, 3, 4, 5. And here's your stereo center right here. And likewise, the other stereo center will be right here. I moved the chat box around. It doesn't really like that for some reason. I put the chat box on another display. I go 1, 2, 3. It's to be R, then this obviously has to be S. All right, so can 2-chloro-2,3-dimethylpentane exist in an octally active form? And the answer is yes. You can see we have an R and we have an S, so it can be octally active. And we'll do question 18, and then we're going to take a break. We'll take our break after 18. 18 says, consider a solution that contains 62% R isomer and 38% S isomer. So we have 62 R, and you may have something different. That's why I'm writing out my numbers. I have 38 S. If the observed specific rotation of the mixture is negative 73 degrees, what is the specific rotation of the pure R isomer? So the enantiomeric excess would be 62 minus 38, and you may have different numbers, so please be sure to check that. I can do this in my head. I get 24. We have 24, and this is R, this is S. We have 20. I have 24% excess R. So to get the pure enantiomer, we're going to multiply the this times 100 over this excess right here. I'm going to put the excess here, and whatever you get, and I get negative 304 degrees. So I'm going to leave my work up there. If you have different numbers, all you have to do is input your numbers where I put mine. You should get the correct answer. I'm going to go ahead and I'll share my screen, but I'm going to pause the recording. We are going to take a break. All right, I'm back now. Hopefully you enjoyed your break. I know I did. I made it back to Kentucky on Monday. I actually drove back on Saturday. So I'm back in Kentucky. I'm in my office. So if anyone is in, at EKU, can come by and say hi to me in my office. So we'll go ahead and get started. Again, we'll continue on. We left off on question 18. I'll start sharing my screen where we left off. And because of these updates that EKU is doing on my computer, it is slowing down my computer a little bit. So I apologize for any, slowdowns that are happening or any delays. There's nothing I can do about it. It says Windows upgrade is 77% updated. So I just have to live with it. So question 18, everyone should have got 100% on that one. We'll go on to 19 now. So question 19, it says an attempt at synthesizing a certain optically active compound resulted in a mixture of its enantiomers. Okay, so we get a mixture. The mixture had an observed specific rotation of plus 11.6, so observed specific rotation. If it is known that the specific rotation of the R enantiomer is negative, okay, so the known R, I'm just going to put the known R, that's my abbreviation. Known R is negative 29.2. Determine the percentage of each isomer in the mixture. So we have alpha of the mixture. I can see where the delays are happening because when I write, it's delayed on writing on the screen because of these updates. I do wish the updates would happen, at night, not during the working day. So the alpha of the mixture is 11.6 equals X times negative 29, because this is the R known, 2 plus 1 minus X, we're solving for X, times the 29 that we have here. And this is the, so if the alpha of the, if the known for the R is negative 29.2, then the S would be the opposite, and that would be 29.2. So, oh. So we just have to solve for X here. You know, you just use the distributive property, and I get X equals 0.301. And this is the fraction of R isomer in mixture. And to get that in a percentage, you have to multiply this by 100, right? So to multiply that by 100, you get 30.1%. So the fraction of the S, if you know the fraction of the R, you just take, you know, let me see, you just take 100% minus that. So whatever, 100 minus 30.1, you don't have to use a calculator for that. 70, so 69.9%. And this is the fraction R, and this would be the fraction S. Any questions on 19? So I'm just gonna, you know, reiterate, if you are listening asynchronous, I know everyone listening synchronous is doing their homework, but if you are listening asynchronous, please just, you know, you got to do your homework, you know, so just make sure that you get your homework problems done. I'll send out an email reminder today, you know, saying that the homework is due tonight, but just please, you know, just work on your homework, get it done. That way you don't have to worry about missing points on your homework. So that was 19. Let's go to 20. It says indicate the relationship of each pair of compounds. You might find it helpful to make a model. So if you have a model, this is where the model is going to help you out. I should say a model kit, not a model. I mean, it's who would have these exact models already built. Here's pair 2, so I'm just gonna, I should have put it like that and just did this. So the first one's gonna be identical. You can, if you flip this around 3D, you're gonna see that it is identical. The pair 2, this is not gonna be identical, and these are gonna be enantiomers, so that means they're gonna be mirror plane. You just have to flip one 180 degrees to see that. So these will be enantiomers. And this is where the model kits really help out to visualize this. That's 20. For which one does it say? Are you talking about question 20? Question 19. Did you have the same exact numbers I did? Because when I re-click on the question, now I get different numbers right here. I have different numbers, so I'd have to go through it. So you're going to have different numbers than me on this one. So you're going to have a known R. You're going to have it. You're going to have some type of observed rotation here. So So you're gonna have, so everyone's gonna have different numbers. And if you re-click, and this is a thing, let's just say you have the same, you have the numbers I did. I know you won't have the same numbers, but let's just say you did, and you go back to 19, you're gonna have different numbers on question 19, even though you solve for these numbers that I show on the screen. So every time you re-click on 19, they're gonna be different numbers. So that's a good question. So let's go on to question 21 then. I hope the system doesn't restart on me. That's what I'm hoping for. So if it does restart, you know, just give me a minute. I'll be back. I don't know what's going to be going on with this system update. It's an unknown to me. So question 21, we're given two compounds. I'm just going to draw them the way that